Hello, and welcome back. Today we're going to continue our study of functions. So as we learned in the previous video, functions take an input, they do a process, and they yield an output. They are the machines of the mathematical world. So the way that we notate functions is we say f of x is a function. This says that I'm naming my function f. It has one parameter, which is an input, that's going to be called x. And then on the other side of the equal sign, I tell you how we're defining this machine to work. And this can be anything that we want on this side. So this is, let's say this is x squared plus 5x minus 3. Okay? So we have a function that takes x as a value, yields the value of that value squared plus 5x plus 3. So f of 2 is equal to 2 squared plus 5 times 2 minus 3, which is equal to 4 plus 10 minus 3, which is equal to 11. So here you have the input. We give it the 2 at the input. It processes it. And then this is the output. And it basically replaces f of x anywhere we have it. So in the last video, we went into functions pretty in depth. In this video, I want to talk about something called an inverse function. Okay, so if you imagine a function being a machine, an inverse function is what happens when you run the machine backwards, right? That is, if I want to take my output and find my input. So how does this work? Well, let's say that we had a function f of x equals 3x plus 5. Okay, so let's say I put a 2 in. So I say f of 2, give me 3 times 2 plus 5, which is equal to 11. Okay, so what I want is I want to find a function that if I give it 11, it'll spit back 2. Okay, so that is known as the inverse function. And we write the notation for an inverse function is like this. Now this -1, it's not an exponent. It looks like an exponent. It's in the position of an exponent, but it's not an exponent. It means that this is the inverse function of f. Okay? So what we want to do is figure out what would be a function that, if given the output of f of x, would give us our input. Okay, so how do we find that out? Well, if you think about it, in this case, x is our input and f of x is our output. So what we need to do is simply solve this equation so that x is our output and f of x is our input. So what we'll do is we'll treat f of x as if it were just a variable like y. Okay, so we can say, so what we want to do is we want to isolate this x all alone so that it is our output rather than our input. So what we can do is we can subtract 5 from both sides. And then divide both sides by 3. And so this will get, say, f of x minus 5 over 3 equals x. So what we usually do now, because we want to write this as an inverse function, since this is now our input and this is now our output, we then write them as such. So we say f inverse x is equal to x minus 5 over 3. So this is our inverse function. Okay, so it has, so if we're given this as an input, this is the processing to yield the output. So let's show that. So if we have, let's go over here. If we have f of 4, okay, well, that's 3 times 4 plus 5, and that's going to equal 17. Okay, so now let's run 17 through our inverse process. Okay, that says we're going to take it 17 minus 5 divided by 3. That's 12 divided by 3, and that is 4. So you can see that our input to our first function is now the output of our inverse function. Okay, so input gives us an output, and if we take that output and put it into the inverse function, we'll get our original input back. Okay, and that's true for anything that we pump through this. And so this leads to something that's very important. It's very simple, but it's very important. And that is, if we have a function, f of x, and we have the inverse function, inverse of f of x, okay? If we have those two functions, then if I say f of the inverse of x, that gives me x back. So likewise, if I do the inverse of a function, I get the original value back. So let's interpret what this means. So f of x means we're going to run a machine. Okay, so we run a machine and we get an output, and that output goes here. Well, what does inverse f do? Well, inverse f is the same machine, but it's what's happened when you run it backwards. So inverse f is going to run it backwards and take my output and give my input back. Okay, so if you run a function and then run its inverse, you get the original value back. And likewise, if you run the inverse function and then run the main function, you'll get the original value back. Okay, so these two are very important. You'll use them a lot. In fact, we already use them a lot. If you think about it, if you have multiplication, right? Well, how do you unmultiply? Well, you divide. How do you unadd? You subtract. And so you can think of those as being in inverse relationships to each other. So this is just a more general way of discussing that, because with any operation in mathematics, we need a way to do it, and we need a way to undo it. And so the way that we talk about that in general terms, f of x does the thing, inverse f of x undoes the thing. Okay, and we can even see that if you've done trig, you've already encountered this with sine and cosine. So if you have sine of x, that will yield a value, okay? But you can invert that. If you do inverse sine, this has other names too. The The inverse functions, also known as arc functions. So arc sine is the inverse of sine. These two are the same thing. I think of it, the way that I think of it is that arc sine is the arch enemy of sine. It undoes everything that sine does. So arc sine of sine of x, both of these give back the x, because this does the sine and this undoes the sine. Okay? So, and these are the same thing. Now, there is a bit of an issue in that functions, in theory, are supposed to only yield one value. Okay, now, they don't, there are more exceptions to this than the rule, but the way that you're supposed to think about functions, at least, is that they only yield one value. And so if you think about our functions, if I say f of x equals 4x minus 2, okay, well that yields one value, and its inverse also yields one value. But for more complicated expressions, so let's look at f of x equals x squared. Okay, now here, the function will only yield one value because any value only has one square. But the inverse function, let's look at how you would do an inverse function. Okay, well, basically the only thing that you have to do here is to take the square root of both sides. So the square root f of x equals x. So we can rewrite this as okay, so the inverse function is the square root, but the square root has both a positive and negative value. So this, it looks like a function, but it actually has two results. Okay, so if I say f of 2, I do in fact get 4, but what happens when I do the inverse function? Well, 2 is one of the values I get back, but I also get back negative 2. And so, so this isn't a terrible atrocity, but it's something to keep in mind. And that is, if a function yields more than one value, it can kind of trip you up. Because if I run the inverse function, now I'm getting not my input back. See, my input was 2, my output includes 2, but I also have this other straggler coming along as well. Okay? So as I said, that's not terrible, but it does complicate things a little bit. So what we've dealt with so far are explicit functions. So what we've dealt with so far are functions where we give the function a name. But sometimes functions are more of an idea rather than a named entity. So for example, if I say y equals x squared plus 2x, well here we can see that this could be written as a function. It's a machine that has one input. So I can say that y is a function of x because y is determined by x's value. And so I can write this as saying y equals f of x, and then I can say f of x equals x squared plus 2x. And you might say, well, that's a lot of extra work. Well, sometimes just doing a little extra work gains you things in the long run. The important thing about this is that we can use this to generalize some facts about y. Okay, so here we have the very specific statement, y is equal to x squared plus 2x. Here we generalized it and just said that, well, y is a function of x, which means that if we know x, then we can know y. And so we're able to use that to say, what about other variables? Do I need to know other variables to know y? No, I don't. I only need to know x. And so I can summarize that by just saying y is a function of x. So you can also find functions. So you can use functions not only as the entire right-hand side of an equation, but let's say that we had something like y equals x squared plus 3 over x squared plus 1. Okay? Now, what I might want to do is I might want to simplify this. And one way to simplify it is that notice that x squared plus 3, I can separate that 3 out into x squared plus 1 plus 2. And if I do that, then I notice that I have similar things on the top and the bottom. So I can say f of x equals x squared plus 1. So I'm creating a machine and defining what it does. And so now I'm going to write y in terms of my machine. Now this doesn't give us a lot of practical utility now, but the point is to think about when you look at equations, are there pieces that we can pull out and make use of? So I'll show you a place where this is helpful. So let's say we had the equation sine x squared plus 2 sine x plus 1 equals 0. Now take a look at that for a minute. Does it remind you of something? Well, notice we've got a squared term. Then we have a not squared term. And then we have a number. And they are all set to 0. So this looks a lot like a quadratic equation. But the problem is that we have sine x where we would normally just have x. So what can we do about that? Well, we can recognize that sine x is a function. Okay, and so what we can do as mathematicians, you're allowed to create functions, variables, anything, as long as once you create it, you leave it the same throughout the rest of the problem. So in this case, what we'll do is we will say u equals sine x, and we would just say that, right? We don't have to justify things that we make up. We made up u. We can do it for any reason we want. But the nice thing is, if u is equal to the function sine x, then we can replace sine x, because anything that's on opposite sides of the equal sign, since they're equal, they're equivalent, and I can replace them for each other. Okay, so that becomes u squared plus 2u plus 1 equals 0. Now that, and I don't need the parentheses anymore, now that is a quadratic equation. Okay, we're just using u's instead of x's, which the formulas don't care. You can use u's instead of x's all day long. So we can use the quadratic formula to solve this. So we can just say u equals, now if you haven't memorized the quadratic formula, you should do that. It's very important. It will, most of math eventually comes back to using the quadratic formula. So if you remember, you put the coefficients, there's an implicit one here of 1, a, b, c. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And that is equal to negative 2 plus or minus the square root. 2 squared is 4. 4 times 1 is 4. All over 2. Now this becomes 0. So adding 0 to something or subtracting 0 from something does nothing. Negative 2 over 2, these cancel, yielding negative 1. So u equals negative 1. Are we done yet? No, because we're originally trying to find x, but what we actually found was u. So we found out that u equals negative 1. Okay? And it's always tempting for people to stop when they have an answer, but in this case, it's not the final answer because we're looking for x. But since u equals sine x, we can replace u in this with sine x. Okay, so sine x equals negative 1. Well, what do we do when we have a function and we want to reverse it? Because we want to get x by itself. Okay, well, what you do is you always just apply the inverse function. So we're going to do arcsine of x, but that means you can do anything to an equation as long as you do it to both sides. So don't forget to do it to both sides. So arcsine of the sine of x, well, given this as an input, so this arcsine undoes the sine. So this will come back as x equal to, and so you can use your calculator for this, arcsine of negative 1. Now it'll give you one of two answers. It'll either give you negative 90 or negative pi over 2. Now the reason for that is because your calculator may be in degree mode or radian mode. So this is the answer in degrees, and this is the answer in radians. In calculus, we prefer radians. And the reason for that will happen much later in the course. But radians simplify a lot of different calculus operations. So we will say that our answer is negative pi over 2. But the one problem with that is that arcsine does not have one output. It actually has infinitely many outputs. So arcsine, the output of arcsine repeats every 2 pi. So so it can be any multiple of 2 pi added to that. But generally, we think of the primary solution as just being x equals negative pi over 2. Okay? So, anyway, so this is how you use functions, because what we did is we transformed this guy, and we recognized that this sine x, it was occurring over and over again, and that we realized that this almost looked like a quadratic, except for the fact that it was sine x rather than x. And so we used our ability as mathematicians to define variables as functions, functions of variables, to replace that with just a u. And then we're able to solve it. So now, for our final topic with functions, I want to talk about implicit versus explicit functions. And what we have been doing so far, we've been focusing on explicit functions. And this is where you can actually write out, f of x equals x squared plus 3. We wrote out the machine for the function. That's an explicit function. But on an implicit function, what we do is we intermix the outputs and the inputs. And so to see what that looks like, let's say we had xy equals 5, where x is the input and y is the output. Okay, so this actually is a function, but it's given implicitly rather than explicitly. Okay, because we've intermixed together our inputs and our outputs. Now in this case, it's trivially easy to solve for our output from our input. So we can divide both sides by x and say y equals 5 over x. Okay, so now this is an explicit function of x. We can see our input and our output. F of x equals 5 over x. So our input, our processing yields our output. But this is another valid way to write it. It's just this is an implicit way of writing rather than an explicit way. And some of them get even more complicated. For example, if you imagine x squared plus y squared equals 1. This is an implicit function, and to solve it, you actually have to do quite a bit of messing around. We can say y squared equals 1 minus x squared, and then y equals the square root of 1 minus x squared. Okay, but they can actually be so complicated that you can't actually solve in an explicit fashion for the function. So the last thing I want to go over is what a function looks like graphically. Okay. So a function we can represent on a coordinate plane. Now, if it has one input and one output, we can do it on a two-dimensional graph like this. But if it had two inputs and an output, we would need a third dimension. If it was three inputs and one output, we actually couldn't draw it because we can't draw in the fourth dimension. We'll say that x is our input and y is our output. Okay, so let's use the function f of x equals 2x minus 1. Okay, now f of x, we usually graph the output of the function as our y value. So this would be the same as saying y equals 2x minus 1. Okay, so given the input of 0, the output will be negative 1. So 2 times 0 is 0, minus 1 is negative 1. So for an input of 0, we get an output of negative 1. For an input of 1, we get an output of 1. For an input of 2, we get an output of 3. And this will form a nice straight line like this. And it will go on forever in both directions. Okay, so this is a function, and we can tell that every input has exactly one output. How do we tell this? Because if we draw vertical lines, we can see that it intersects our graph at most once. And that's kind of the ideal situation. Now, we dealt with a function earlier, actually several of them, where this was not true. For example, when we had the implicit function, x squared plus y squared equals 1, that actually forms a very small circle right here. Okay. Now it doesn't matter the fact that if I draw a vertical line here, I don't intersect anything. That just means that the function isn't defined at that point. But the interesting thing is here, if I draw a vertical line, I actually intersect my graph 2 times. And so that means that given a particular x value, I can't tell which y value it should be. Now, as I mentioned, this doesn't cause too many problems as long as these points are separated. Most of the theorems about functions are still valid if you have more than one output, as long as those outputs are sufficiently separated from each other. And by sufficiently separated, I mean that you could zoom in close enough that it looks like, given one input, you'll get one output. And to see what I mean by that, imagine instead if this whole circle were filled in rather than it just being a line. So here, not only is my line intersecting infinitely many points through the circle, but there's no way to zoom in close enough so that it only intersects once. No matter how close I zoom in, it's going to look like this thing is intersecting more than one point. So that does not work with most function theorems. Okay? So that's functions. As a quick recap, functions can be implicit or explicit. They are machines that take an input, they do a process, and they yield an output. An inverse function is written like this. And an inverse function undoes the action of the machine. So it's kind of like running the machine in reverse. And so if I take a function and I do the inverse, I will get back my original value. Thank you for watching. I hope to see you at the next lesson.